So we're going to start talking about soil colloids. This is, I think, chapter 8 in your book, depending on which edition you have. So just make sure you check the table of contents for the chapter. We're going to learn how to characterize soil colloids with respect to their size, surface area, surface charges, the adsorption of cations, and the adsorption of water and different types. We are going to talk about tetrahedral and octahedral sheets along with the concept of isomorphous substitution. We're going to teach you how to correctly identify kaolinite, smectite, vermiculite, and fine-grained mica, either from descriptive information or from an image, but most likely from descriptive information. We're going to talk about iron and aluminum oxides and humus, not hummus, which is delicious with 2 M's. Humus just has 1 M because it's not tasty at all. It's found in soil. So we're going to talk about whether or not colloids have negative or positive charges. We're going to talk about something called constant or pH-dependent charge. We're going to talk about 6 principles of cation exchange reactions. We're going to define cation exchange capacity. And we're going to talk about soil pH. So an overview of where we're headed here. This is a clay particle. And basically what we find as we zoom into the chemical structure, the crystalline structure of these clay aggregates and particles, is that they're made up of sheets of crystalline structures, and in between each sheet is an interlayer space in some types of colloids that provides more surface area for holding onto plant nutrients or water or whatever may else be attracted to those spaces. And so this chemistry of these surfaces becomes important to understand so that we can understand how soils are going to interact in certain conditions where they have certain types of nutrients or lack thereof. So characteristics of soil colloids include their size. Their size is 0.002 millimeters in diameter or smaller. They tend to be very small, okay? And as we know, when you get something super small, as particle size decreases, the surface area increases. They also have charged surfaces. Most of them have a negatively charged surface, so we will learn later on about some that have a positively charged surface. They have adsorptive capacity, meaning they can hold on to things at their surface sites, kind of like a post-it note, and exchange them for other post-it notes in various environments. And here's just some really cool scanning electron microscope images of a variety of soil colloids that we're going to learn about. So there's different types of soil colloids. By definition, a colloid is anything dispersed in air or water. So we're talking about soil clays, basically, that are dispersed in air or water. So the different types of these clays that are dispersed in air or water are crystalline aluminosilicate clays. These are well ordered. An example of this is kaolinite. We'll learn a lot more about kaolinite later. Some non-crystalline silicate clays are similar to what's listed above, however, they're not well ordered. They can have positive and negatively charged sites on their surfaces. An example of this is allophane. Iron and aluminum oxides are very important in highly weathered soils like ultisols or oxasols, and they contain minerals like gibbsite and goethite, whilst others are amorphous and occur as coatings on minerals. Humus is an organic colloid, okay? It's really important in the upper parts of the soil. It's not a mineral or a crystal, but it basically has an undefined structure. It's basically plant schmutz that's really, 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 really tiny, okay? So it's like the elemental compounds of plants, and we'll learn more about that later on. So let's talk about the layered silicate clay structure. Here we have the building blocks of these clay sheets, all of these sheets that stack up to make a clay particle, okay? So we're going down to the building blocks of what's in those sheets. And there's 2 parts. There's going to be tetrahedras, which are 4 oxygens surrounding a silica ion. And these combine to make a layer called a tetrahedral layer. We also have octahedra making up the sheets in the layered silicate clay structure. Um, and the octahedra are basically 6 oxygens surrounding a magnesium or an aluminum ion. And these connected together make a layer of octahedra. So then we have a layer of tetrahedra and we have a layer of octahedra. And what we're later going to learn is that the number of each type of these layers helps define what clay we are actually dealing with. So again, the building blocks are the tetrahedra and the octahedra, and the tetrahedral sheets usually sandwich the octahedral sheet, and then there'll be an interlayer space before the structure repeats. And it's really important for you to know that silica or silicon is associated with the tetrahedral sheet, and aluminum or magnesium, but most of the time I refer to aluminum as being associated with the octahedral sheet. So if on an exam I say, which element is associated with a tetrahedral sheet, you'll say silicon, and which layer is associated with aluminum, you would say octahedral. So we've kind of learned basic information about the crystalline structure of clay. So let's start learning about how we get those sources of charge, and basically the sources of charge, these little charge sites that are on the edges of soil colloids. This is where soils are able to hold nutrients like nitrogen or sulfur or phosphorus or potassium or anything else. These charge sites are basically parking spots for things that interact with soil. Um, they're basically able to absorb ions. Okay, so understanding these charge sites becomes very important. And there's 2 types. Okay, so clay falls into 2 categories. They either have pH dependent charge sites or they have permanent charge sites. Let's see what those are. A pH dependent charge site is basically the edge of the ion has some hydrogen ions, and when those hydrogen ions dissociate, meaning they get kicked off, they leave behind a negative charge site. And so in this instance, as pH increases, we get greater negative charge. And generally this is anything above a pH of 3, 3.5 will be negatively charged. So as pH increases, deprotonation increases. So for those of you who aren't sure what deprotonation means, when we refer to these hydrogen ions, these little H's, they're called a proton. And so when they're kicked off to create that negative charge site, we call that deprotonization because we're deprotoning it. Okay, so that's where that word comes from. So in this instance, pH can change the actual number of charge sites. So again, in a pH dependent clay, you're going to see a lot more negatively charged sites the higher the pH. And what we'll later find out, because of this characteristic, this pH difference in charge, that means that there's going to be some ions that at really low pHs, they can have a positively charged surface. And this is kind of rare, okay? Most of the time, soils are negatively charged. So
So
again,
now
we
I
see
want
an
to talk to
example
you
of
about
trioctahedral
permanent
versus
charge, okay?
dioctahedral,
And
where
this
the
is
octahedral layer in
essentially
the middle and
going
the
to be
trioctahedral
created
has
by a
3
phenomenon called
cations. As you can see,
isomorphous
the spots
substitution.
in the
So we talked
middle,
about
what
how
look like little drums,
potentially,
versus
the
the
tetrahedral
dioctahedral on
layer
the right, where
always has
only
silica,
2
and the
spots out
octahedral
of the
layer either
3
has
in the middle
aluminum or
little drum-looking
magnesium.
things
Okay. Well,
are filled.
sometimes
Okay.
in the crystalline structure, those things get.
So the way that these isomorphic substitution phenomenon kind of works in these permanently charged ions is usually it's going to have a switching out of a similar radius ion. Okay, so for example, um, iron and magnesium are very similar in ionic radius, so usually they would swap out for each other. Um, the same thing as you can see in the tetrahedral sheet, these three are the most commonly swapped out. Silica, aluminum, and iron can all isomorphically substitute for each other depending on the clay that we're looking at. Whereas the octahedral sheet, anything from aluminum down to iron. And then we can see all the ions that exchange throughout the exchange sites, which are those negative charge sites that are created on the outer edges of the particles. These are our parking spaces for nutrients. All right, so now let's start determining the difference between all of our clays. Now that we've learned where they get their charge from, let's learn how they all stack and create their own crystalline structure. So we have a one-to-one layered silicates, which just have one aluminum sheet and one silica sheet, meaning one octahedral and one tetrahedral sheet. That's why they're called one-to-one. A 2-to-1 layered silicate has two tetrahedral sheets with an octahedral sheet in the middle. It's like a peanut butter and jelly sandwich. Okay. And so the bread would be the tetrahedra sheets with the silica, and then the peanut butter and jelly would be the aluminum sheet in the middle. Okay. And so these are our two generally common type of crystalline structures: our one-to-one layered silicates and two-to-one layered silicates. And if you look on the right side of both of these examples, you'll see that I've simplified the drawing to just a box. If I ever ask you to draw these, that's all I'm looking for are these simplified boxes. I don't want you to draw all the individual ions or anything like that. What's interesting about one-to-one silicates is that because they have a silica sheet that from the first layer that will attach to the aluminum sheet of the second crystalline layer, we end up having hydrogen bonds forming in between layers as they stack up, and so they're held very strongly together. So they don't expand. So these type of minerals we don't see expanding when you add water, for example. So we're going to start talking about the one-to-ones versus two-to-ones that are either expanding, meaning they can open up their interlayer space, like Hungry Hungry Hippo, or if they're non-expanding, there's something in that interlayer space that's holding them together. So here again, we see a one-to-one. Okay, so we have our silica sheet and then one aluminum sheet and an interlayer space, and then the structure repeats itself. We have one silica sheet to one aluminum sheet. And please remember, the silica sheet is tetrahedral, the tetrahedral sheet, and the aluminum sheet is the octahedral sheet. So these are one-to-one layers. Okay, and they're held together by hydrogen bonds in their interlayer space, so they don't expand or anything. So some really good examples. The most common example of one-to-one clays is kaolinite. I definitely asked about that on the exam. Colloisite is another example. And here's what they look like under a scanning electron microscope. They create these really cool stacks because of those hydrogen bonds. They really hold them together in like these neat little stacks, like booklets almost. So you can see here all the sheets held together. So the one-to-one clays, because they have hydrogen bonding, that interlayer space is not available as surface area. So they have very low surface area. It's just the edges and any exposed surfaces. So very low surface area, very low water holding capacity because they don't expand to open that interlayer space at all. Those hydrogen bonds keep them close together. They have very low negative charge because there's not a lot of surface area that's charged. They are a pH dependent charge. Okay. Very little isomorphic substitution, which is why they're a pH dependent charge. These are relatively easy to manage soils. There's not a lot of shrink or swell going on. I'm just gonna check on my comments, make sure no one's asking questions. So now I'd like to talk about the 2-to-1 non-expanding clays. Okay, so a 2-to-1 again has two tetrahedral sheets and one aluminum sheet sandwiched in the middle. Okay, so we have one tetrahedral sheet up here, and then an aluminum sheet, and then a silica sheet. And then in the inner layer space, before you start the next row of sheets, the next 2-to-1 layer, there's potassium holding the layers together. So this is why it is non-expanding, because that potassium keeps those inner layers together so it cannot open up like a mouth, okay? So the only thing in their inner layer space is potassium. So they don't expand. Some examples of this are fine-grained micas and chlorite. All right, so some facts about the 2-to-1 non-expanding fine-grained mica. It has a moderate surface area, moderate water holding, slight swelling, but not a lot. Moderate surface charge because of some isomorphous substitution of aluminum for silica in the tetrahedral sheets. The charge is around 40 centimoles charge per kilogram of soil. And management of these soils are relatively uncomplicated because they really don't swell that much. They've got that inner layer of potassium holding them together. So they're relatively uncomplicated to manage. Now we're going to start talking about our 2-to-1 expanding smectite. So again, we have a tetrahedral sheet with silica, and then an octahedral sheet with aluminum, and then another tetrahedral sheet, and that's our 2-to-1. But this time, we don't really have anything in the inner layer space. It can open up to grab whatever it wants. And because of this, especially when you add in water, it swells super, super big. So these soils are really awful to manage, and we call them smectites. Sometimes you'll hear me refer to them as montmorillonite, which is a type of smectite. So again, we've got 2-to-1 layers, but the inner layer space can open and expand and pull in whatever it wants. Think of it as like a big hippo mouth. And it can pull in water and it can pull in nutrients, and it expands significantly. So because of this inner layer space being available, and opening as wide as it wants, basically, we have a really high surface area in these colloids. We have very high water holding capacity, very high swelling capacity. We have very high surface charge from isomorphous substitution potential of iron and magnesium for aluminum in the octahedral sheets. The charge is definitely high. Montmorillonite is an example of a type of smectite, and this makes, when you have this kind of clay, it makes management for homes and farms very tough because of the shrink swell capacity. There's another type of expanding clay called vermiculite. This one has a very high substitution of aluminum for silica in the tetrahedral sheet. And so this gives it really high cation exchange capacity, meaning very high ability to exchange things on its surface, exchange those post-it notes that are kind of stuck on those that are associated with those parking spots that are made available. The presence of magnesium and aluminum hydroxide ions and water in the inner layer often prevents collapse, and it holds the layers together. So it has kind of limited expansion. It won't expand as much as smectite, but it'll certainly expand a lot more than like kaolinite would, which is a 1-to-1. So in review, we have our kaolinite 1-to-1 non-expanding, no swelling, one tetrahedral sheet to one octahedral sheet, and then it's held together to the next set of sheets with hydrogen bonds, so there's no swelling, very uncomplicated management. We have our smectite 2-to-1 expanding, which is like the maximum of all expansion. It has a sandwich of an octahedral sheet between two tetrahedral sheets before it has that giant inner layer space. Then vermiculite is a 2-to-1, and it only does some slight swelling, but it still has the capacity to swell. And then we have our fine-grained mica, which is a 2-to-1 non-expanding, because it has those potassium ions that hold the sheets together so that it can't expand. And we didn't really define chlorite, but chlorite is another 2-to-1 with minimal swelling because it has a hydroxide sheet in its inner layer that kind of keeps it from doing too much. So now we're going to talk about the structure and charge characteristics of non-silicate colloids. So we're going to be talking about aluminum and iron oxides and organic colloids. So aluminum and iron oxides are basically octahedral sheets that are left over after a whole bunch of weathering. So the tetrahedral sheet has been weathered off, and part of the octahedral sheet has kind of undergone weathering and is a little messed up, basically. We refer to these as having low solubility. We call them stable minerals because they're the end of the weathering sequence and they can't really become anything else. So that's why we call them stable minerals with low solubility. So aluminum and iron oxides are stable minerals with low solubility. I'm pretty sure that's an exam question. So these end up being pH dependent for their charge. So in acid soils, they might even have a positive charge. So if you get the pH low enough with aluminum and iron oxides, you could get a positively charged soil, which is hard to find. So this is kind of one of those fun little facts. Most soils are negatively charged, but these are the only ones that at really low pHs they can have a positive charge. So we're also going to talk about organic colloids, which is humus, not to be mistaken with hummus, because hummus has two M's, and hummus is delicious, and humus is not delicious at all because it's found in soil, and if you like eating soil, you have a condition called macrophagy, and you need help. So, anyways, organic colloids are basically these are weathered plant materials. I mean, they're a bunch of like carbon functional groups. This is kind of like our guess at what the structures may be. You see this long organic looking weirdness. Um, it's going to have a very high negative charge. It's going to be pH dependent because all of those functional groups all over this thing, they're all going to have pH dependent pH dependent protons that can be kicked off to create a charge site. Okay, so it's pH dependent, and it can have tons of charge sites available. So that makes it very good at holding water. So very high water holding capacity, very high surface area, and very important relative to clays because what we found is that organic colloids like this one generally attach to the surface of clay colloids and extend their surface area and really control a lot of the surface chemistry. They're very interesting to study. And of course, they're all different. So that's why they don't have one defined structure because we don't know what kind of plants have really contributed. Every environment has different types of plants, and so they're gonna have different functional groups and a different structure for their organic colloids. So there's really not a defined structure. So I'm never going to ask you to draw an organic colloid structure ever, not one time, okay? Because there is not any one structure. All right, so these functional groups that we see on the edge sites of a large complex organic humus molecule, um, it's consisting of chains and rings and carbon and hydrogen atoms, and then we might see some carboxyl groups or some phenolic hydroxyl groups or some alcoholic hydroxyl groups associated with the surface. And these are all the types of groups that are going to deprotonate and provide some kind of surface charge for ions to interact with. So here we can see an example of carboxylic acid deprotonating as the pH increases and creating a negative charge site on the humus molecule.